Anything works, and a lot of my work has been inspired by a lot of his work. So, and I mean, Nitin is already super famous, so I'm not going to spend half an hour introducing him, but some of his most famous prizes are the Godot Prize and the Focus Prize. And today is going to talk a little bit about the border and demystifying the border for all of you guys. So please, welcome, Nitin.
Yeah, thank you. So I especially thank Rafael for organizing this trip. We have been planning for at least 1 year. And he has an excellent team, especially Isabel is here, who helped organize everything perfectly. And it's very efficient and beautiful. And this is my first time in Canada. So I think I waited for the right time to visit Canada. I'm happy about that. Thank you for coming so early in the morning for this talk. This has a lot of things. I was not very much clear about my audience. But there is no hurry to finish everything, so you can just interrupt me and ask questions. So you can interrupt me anytime, don't wait for the end of the talk. So what I will talk about is... so
can't see the screen very well.
Oh, I think in the next it'll be fine, because then it'll be black and white, yeah. Oh, you want to remove this screen? Sure. That should be fine, I think, most of the time. So I'll define what I mean by border, but this is something to do with the computational complexity classes and then taking limits. Okay, so I'll define this formally. And our computational classes will be computation will be algebraic in this talk. So this is based on many joint works with my PhD students, Pranjal, Pratik, and Bhargav. Okay, so what is computation? In this talk at least, so that it is formalized by what a Turing machine does. Okay, so Turing machine is just, it's kind of a C program. So if you look at the operations in a C program, then they are being computed by the finite control, which is the processor. And then all the data is being written on a tape, which is an infinite tape. It's basically the hard disk or RAM. And then every step is very simple. So head either moves left or right. It can edit the cell. So every step is very simple, but then as you all know that when the process ends, something big has been solved, right? So that's the idea of breaking computation into small steps. But we'll not do that in this talk. But it's a good way anyways. It's a good starting point. So Turing machine defines computation, and anything that is done on a Turing machine is basically a computer program, which you can directly implement on a physical device also. And mathematically, it gives you a perfect formalization of problems. So a problem is basically just a set of Boolean strings. Okay, so what is being computed is whether a string is in a language or not, whether a string is in a set or not, and that set is your problem. And then once you have this program executed on a Turing machine, you can ask about the resources. So how much time it takes, which is how many steps the head moves, and how much space, which is how many cells on the infinite tape were used. Never the infinite tape will not be used fully ever, because the computation is finite. So you can count how many cells were actually used. That's the space complexity. Yeah, but in this talk, we'll do something else, which is modeling computation via a circuit. So this is a much relaxed variant of a Turing machine. So it looks like this in this talk. You have variables in the leaves, and then you have addition, multiplication gates, and so ultimately a polynomial is computed at the root. And on the wires, you can put field constants, like you can put -2 or square root 2 or e or pi or whatever. The interpretation is that whatever comes out will be multiplied with that constant. Right? So this is a complete model. It computes every possible polynomial. It cannot do infinite sum, so it only computes polynomials. It will not compute power series. And it will also not do division. So there are two kinds of circuits. In this talk, we'll only talk about algebraic. So this is called an algebraic circuit. But the circuit that came first was the Boolean circuit, but we'll not mention it in this talk. Boolean circuit is closer to the Turing machine because the strings were Boolean strings. But that's not our model. So here we'll actually be computing polynomials as a whole. We'll not be evaluating them. Okay, so the polynomial will be computed as a function in n variables. So that's the algebraic computation, algebraic circuit model. Computes the polynomials little f in n variables x1 to xn. These terms I will consider self-explanatory. So node, these are nodes. They have operators in them. Edges have constants on them. Leaves are the variables or constants, and root is the output. Okay, so this I need to define the resources here. So the resource concept is size, which is how big this graph is. Okay, so number of vertices and number of edges. Note that we don't talk about the constants. So constants, even if they are very, very large, they are not counted. Okay, only the graph size is. So this is size of a circuit. And second important resource is depth, which is like depth here is 1 and 2. Okay, so there are 2 edges. The longest path has 2 edges from leaf to the root. That is somehow, I mean, if you actually fabricated this in practice via chips, then how many chips have you used and how many wires, that is the size. And the depth will actually represent time in seconds. So how much time it took to do the computation. Right, so that is what depth is. And size is kind of the space, how much space your computer takes if you actually fabricate this. And now we can actually define how easy or hard a polynomial is. Your favorite polynomial f in n variables. Size is the minimum circuit size that exactly computes it. And VP is the class of all such polynomials. Okay, so VP is the class of easy polynomials. What does easy mean? Easy means that the size of the polynomial, of your polynomial, and the degree, both of them are polynomial in n. Polynomial, so this acronym here is just, it just means n to the constant. Okay, so n to the 100, for example, is fine. But n to the log n is not fine, or 2 to the n is not fine. Okay, so we want both size and degree to be polynomial. Such a circuit should exist for your polynomial. So easy polynomials, practical polynomials are in VP, and what is outside is considered impractical. So size, you may understand, why are we bounding the degree? So for that, you can keep this example in mind. So what is happening in this example is, this is a very simple looking polynomial, except that the x1 here has degree 2 raised to n, which somehow we consider impractical. Okay, so we don't want to look at such polynomials. So we say that this is not in, I mean, this is not in VP because of the condition we have here. Okay, but if it was x1 to the n times x2 dot dot xn, then it will be VP. Okay, so that is the notion of easy and hard for us. Okay, so I think, any questions here? This is just a basic language so that we agree on these terms. So after that, I will just use them freely. So second, so that was one notion of easy polynomials, but we can make it even simpler in the sense that something even faster in practice. So that is called branching program, algebraic branching program, and it will define a complexity class called VBP. It's not very difficult to define. So we can start with the motivating example, which is the determinant. So it's S cross S matrix, big X, which has S square formal variables. And determinant of that, you know, is this expression, right? This is just the monomials given by the permutation of, well, permutation on 1 to S. And then there is a notion of sign of the permutation. So there are odd permutations with sign -1, even permutations with sign +1. So you have this polynomial with +/-1 or 0 coefficients. So that is determinant. It has, I I mean, needless to say, this is the cornerstone of all engineering mathematical applications, because this is the source of all linear algebra, right? So we want to define a way to say that my polynomial can be computed using just linear algebra. Okay, not so. This is a much more special model of computation than what we defined before, right? A linear algebraic model. That is what we'll define. So the other way to do that is using this second problem, which is iterated matrix multiplication. So here you have a product of matrices. These are, let's say, square matrices. And then once the multiplication of the matrices is done, you can say that the 1, 1th, the top left entry that you get is my IMM polynomial. Okay, so that is a polynomial in S square multiplied by D variables. Okay, did not write that. But so the MI has S cross S variables. They are all formal. And then D of them. So D times S squared, that's the number of variables. And the degree of the polynomial is, in this case, it is D, right? Because that many times you are multiplying linear variables. In determinant case, the degree was S. And number of variables was S squared. But so this is matrix multiplication. Many matrices are being multiplied. That's another polynomial. And this again is somehow a practical thing because we know how to multiply matrices, right? So this is another way. And there is a interesting theorem that both these polynomials are easy in the sense of VP also. They are in VP. Okay, so the IMM result is easier because you know how to do multiplication of a matrix by definition. You repeat that, you will get a circuit. Determinant is more complicated. You don't actually see why it should be in VP because you don't really see how to do addition and multiplication on S square variables to get this giant polynomial which has S factorial many monomials. Right? S factorial is much bigger than poly S. So this will need more work. So that is the content of Zanki's proof. But they both of them are in VP, and you can use either of them to define another way to define computation. That's via the ABP model, and where you can just say that my polynomial is of this type, of ABP type, if I can just substitute in these variables linear functions and get my polynomial. Okay, so if I can multiply matrices where each matrix has a linear polynomial entry, and the top left corner computes my polynomial, then I say that my polynomial is easy in this sense, in the ABP sense. So this is also a computational model. It's a bit more direct than the circuit way because you are just multiplying matrices. So it's a bit easier to fabricate in practice. And we can say that the ABP size, so like the circuit size, we can talk about now ABP size of a polynomial, which in this case is S squared dn because that much space it needs to represent in practice. So that is the ABP size. And class VBP is the set of those polynomials which can be represented as this product via this product in only poly n space requirement or ABP size. That's the class VBP. There is a third way to look at this computation, which is maybe a bit easier to visualize. So here you start, there is a start node and there is a source node and there is a target node, so S and T. And in the middle, there are these layers. So this is the first layer, this is the second layer, and so on. Many layers, like in this case, there are D layers. So D layers, and then you can go from ith layer to I plus 1th layer via edges which have linear polynomials on them. And what is it computing? So it is computing, you take a path from S to T, like x plus y times y by 2 times minus x. You take this path, you multiply these linear polynomials. You do this for all paths and then add it up. So sum over weight of paths. Okay, so sum of weight of path, that's the polynomial which is being computed. Why is this an IMM equivalent? It's not very hard to see. matrix multiplication is, it is actually the way matrix multiplication is defined, it's exactly doing this. It's actually giving you all the paths and then summing it up. So these are the three ways to see the same thing. Oh, I have not written that yet, but that's a theorem. It's a major theorem that determinant and IMM models are equivalent. Okay, so whatever you can write as IMM, you can also write as determinant and vice versa. So these are equivalent models. And it's a very nice combinatorial interpretation of the determinant. So this is a theorem by Mahajan Vinay, whose proof is a beautiful combinatorial interpretation of the determinant polynomial. And so overall, what we have concluded is that VBP is in VP. Okay, so all the linear algebraic computations that you do, they are also in implementable via circuit. Right? So if you say it that way, it's not very impressive. But what goes inside these theorems is impressive. And so the open question here is whether these two things are different, okay, which I will read simply as is computing harder than linear algebra. Okay, so whatever you are going to compute ever in life, is it just linear algebra or is it doing something more than linear algebra? So that is the concrete mathematical question, VBP not equal to VP. So can you write any practical polynomial that is in VP as equal to determinant or equal to IMM? Right? I already have written here not equal to because the conjecture is that they are not equal. So VP should have something more than just IMM. Do I have anything else? No. Okay. So any questions till now? I'll also ask general questions. Okay, so that's the definition of VP and VBP. And so those are the practical things. So if there are practical things, there should also be impractical things, right? So we'll define just one class which is highly impractical, at least conjecturally. So that is I'll call it exponential sum circuits, because they are not just circuits. Circuit would have been practical. There is also something very impractical which is on top of them. That is called an exponential sum. So it looks like this. You have a polynomial for which you have a representation of this type. There is a small verifier. I'll call this verifier circuit. So it's a G which is in VP. It has two kinds of variables, X variables and A variables. Let's say X1 to Xn and A1 to AM. But that is not what is computing F. On top of that, there is a sum which takes all values. A takes all 0, 1 values, so 2 raised to m values, and then sums it up. Okay, so it's an exponential sum on the Boolean hypercube of your verifier circuit. So this makes it totally impractical, because even if you fabricate G because it's in VP, but after that you have to sum over the Boolean hypercube. That's 2 raised to m steps. Right, so that's exponential, because m here, think of m equal to n. So this is 2 raised to n. You are essentially evaluating at all possible values. So that is far, far from being practical. But still, mathematically, this can be defined. So we can say that F has an exponential sum circuit. And polynomials of this type, we can say, define VNP class. Okay, that's the VNP class. Why is this useful? So if you have seen this question of counting perfect matchings in a bipartite graph, right? So you have, let's say, in the first block, you have n vertices, in the second block, you have n vertices, and then there are edges. It's a bipartite graph. So how many matchings are there? So that question is a very difficult question. Practically, you cannot do anything. Although you can find a perfect matching, these are famous algorithms since the 70s. You can find a perfect matching, or you can say that there doesn't exist a matching. But then the question of counting all the matchings, because you cannot output all of them because they may be n factorial many, but you can still ask for a number. Is it 0 or n factorial, right? You can ask in the range, what is the number? So that is a hard question. If you can take it as an exercise, it's an easy exercise that question can be written in this exponential sum style. Okay, so this question of counting matchings is naturally of this type, where you can think of G as the algorithm that finds a matching, or that just checks whether something is a matching. Okay, so the G is just verifying the matching, verifying a matching given by A, and then it is just trying every possibility, right? So, and G's output is 0 or 1. So that is what is happening here. But what we are doing is totally algebraic. That there is no, it's not really an algorithm. These are polynomials. But the idea comes from there, from actual algorithms. And yeah, so this polynomial we believe is very difficult. You cannot actually fabricate this in practice in a small size. And I don't think it is easy to see that determinant is also of this type. Yeah, well, from the definition, you can somehow deduce this. But determinant also will be of this type, which is not so interesting because determinant, I already said, is in VP. So it's a practical thing. Being of this type is not that impressive. So, but both these examples are of exponential sum circuit type. And we define VNP via this expression. Any polynomial which has this expression is called the set of such polynomials is called VNP. And in this talk, whenever I say that my polynomial is explicit, I will mean VNP. Okay, so there are polynomials which are explicit, and there are polynomials which are not even explicit. Forget about being practical. So there is practical, there is explicit, and there is non-explicit. Okay, in our spectrum of easy or hard polynomials. So this is the explicit way to define polynomials, or a way to characterize the polynomials into basically 3 classes. Either it's practical, or it's explicit, or it's not even explicit. And VNP is this explicit that I will use. I'll use this concept in this talk. So why is it called VNP? So V stands for Valiant, who invented this. And NP comes from what you have seen in algorithms or complexity courses, non-deterministic polynomial time class. A prime example being satisfiability problem or any kind of optimization problem. They are impossible to solve in practice, and all of them are somehow equivalent problems. So that's where this is coming from. So this is the algebraic version of NP, and the previous thing VP was Valiant speed. It's the algebraic analog of polynomial time. And there are more analogies. So this in NP, there is a verifier algorithm and there is a witness string, or there is a certificate. So that's what we also have here. G is the verification circuit, like analog of algorithm, and A here is the witness variables, analog of the certificate. Okay, so that's the algebraic. You can call it algebraic NP. That's what is happening. And VNP size of a polynomial will be given by this size of the representation, which is how big is G, how big is the degree of G, and parameter N and M. Okay, so that's the VNP size, you can say, of a polynomial.
The fact that we multiply them here instead of adding them before, is it important, or does it
Yeah, no, yeah. So it's just, yeah, we just want an upper bound for all of them. So max will also be fine. And oh, I did not say that, but maybe it is already there in this expression. I'll emphasize it, that, or is it written? Yeah, it's written. Okay. So VNP basically contains all those polynomials whose VNP size is polynomial in the number of variables. Okay, so all these things, size of the verifier, degree of the verifier, and number of variables, and number of witness variables, everything should be polynomial in N. So these 3 things, size G, degree G, and M, those 3 things should be polynomial in N. N is the key parameter, and everything else should be somehow bounded with respect to that. That polynomial is then called VNP polynomial. Yes, so it should be clear to you that there is no reason why polynomials will be of this type, right? There should be, I mean, almost all the polynomials should be outside VNP, right? Because why should any of these parameters be bounded by poly n? It could also be 2 raised to n. So almost everything is actually outside VNP. So almost all the polynomials are actually non-explicit. Forget about being practical, right? This should be immediately clear to you that we are studying something very, very special. The density of polynomials being in VNP across all polynomials is 0. These are very special. These are special things that we study. Just like polynomial time solvable problems, their density is 0. Almost anything in life is complicated. It's not polynomial time, right? So those are very special problems which get solved. Almost everything is unsolvable. So that's the, yeah, and then we are going further down. So almost all the polynomials are outside VNP, but inside VNP, we have a more refined structure. So VNP is kind of these impractical yet explicit polynomials. Then you have practical polynomials, and then you have linear algebra. Yes.
So, sorry for probably a dumb question, but in every polynomial that can be expressed as a sum of monomials, wouldn't that put it in this VNP class?
Sum of monomials, but all monomials, or what is the set of monomials which are present in the support of F? Are you putting all degree D monomials and variate, or just some of them? It will matter a lot. No, so, okay, let me say the positive thing. So if you take all degree D n variate monomials and just take the sum, that will be an easy polynomial. But if you take a random subset of those and sum it up, it will be extremely hard and non-explicit.
Oh, I see. It's the way that G is allowed to end up.
Yeah, so what you have to notice here is that G is common across all A's. As A takes values on the Boolean hypercube, G doesn't change. I mean, the function G is the same. Only its evaluations are changing.
It just fits the bits.
Yeah. Yeah. And exactly the same thing happens with NP also. The verification algorithm doesn't change with the witness or the certificate. Okay. Right. So now, I mean, in this talk, whatever you will ask will be an open question. So for example, now you ask that whether VBP is different from VP, that's open. VP different from VNP, that's also open. Okay, so I say many things, but I know very little. That's my problem. And this, the interpretation of this in English is that is exponential sum impractical. Okay, so if you can write a polynomial as an exponential sum, there should be some polynomial which has this representation exponential sum, but it's actually impractical. Okay, exponential sum is not an indication of practicality, it's the opposite. That is what we are conjecturing. So almost any explicit polynomial should be outside VP. That is what you would conjecture naturally. Just like almost any NP problem will be outside P. Right? So again, in that density of practical polynomials or practical problems should be 0. There should be very, very few problems which are solvable. Everything else is impractical. So that's the natural conjecture to make. I don't think anybody doubts this. But yeah, in this big crowd, maybe 1% doubts. But I think there is almost a consensus that these should be unequal. So this is called the variance hypothesis or variance conjecture. It's the algebraic version of P not equal to NP, okay, for which is also largely believed. But there is no mathematical indication for this. This is just a matter of faith. There is no mathematical indication that these things should be true. Yeah, so variant define these classes, and also then basically it's a characterization. It's a completely new characterization for algebra for polynomials, and then you can formalize these open questions through that. So that's Wheelin's hypothesis or conjecture, late 70s, that there are explicit polynomials that are hard, or as I say, impractical. If explicit polynomials are there which are impractical. That's the conjecture. And a related question here is whether VBP is different from VNP. So that is like asking, is counting harder than linear algebra? Okay, so VNP, remember, it is inspired by counting, and VBP is inspired by linear algebra. So the question is whether counting should be harder than linear algebra. Again, it's I would say a no-brainer. It should be hard, but there is no proof. There is no mathematical, again, no mathematical indication for this, except that, yeah. I mean, the other thing is also true, that there are actually no tools which would suggest or even come close that counting should be possible through just linear algebra techniques. Yeah, so that is the determinant not equal to permanent question. Okay, so permanent, well, I have not defined. I hope you would know this, but if you don't know, then just take the determinant definition and remove the sign. Okay, square the sign. So all the monomials are the same, except they come with +1. There is no -1. Okay, so that expression is called permanent. And this conjecture, VBP not equal to VNP conjecture, is saying that determinant permanent should be different. What does different mean? Different means that there is no permanent in which if you substitute linear polynomials, it becomes equal to permanent. Okay, so determinant model cannot compute permanent. That's the question. That's the conjecture. So, any questions till now? Okay, so we have defined basically three things, VBP, VP, and VNP. That pretty much covers all there is in algebraic computation. So what remains is now to compare them and try to prove special properties of special polynomials. But before that, since my talk had the word border, so I have to define border, or as we'll call it more technically, approximative computation. Okay, so how do you introduce approximation? Just like you have approximation algorithms, where there is some parameter which you are approximating. But those parameters in algorithms are actually real parameters. So with real numbers, you can approximate. Here, I haven't even specified the field where the polynomials live, right? So the field can be finite field. So in a finite field, what is the meaning of approximation? There is no meaning. And also, we are not actually computing a field element. We are computing a whole polynomial in one go. Like determinant is a S² variate polynomial, degree S. So it's not really clear what is the meaning of approximation. So that also requires actually some work. There is a paper which actually defined this, and it's a non-trivial definition with at least 4 interpretations. So I won't have time to go into all of them. I'll just compress this in one slide. So this will be the approximate version of VP called VP bar, where bar is very suggestive, so as you will see. So how to approximate a polynomial is the question. So what we do, I shortcut the whole history and I say that you look at these circuits, practical circuits, which is in VP, that's G, and have a spare variable epsilon on top of your n variables x1 to xn, and then you compute this circuit and then take limit of epsilon tending to 0. Okay. Epsilon is considered as a field element, so there might be 1 over epsilon happening inside the circuit. So 1 over epsilon in the limit will go to infinity. Okay, so that's where the limit is coming from. If it was just a polynomial in epsilon, then obviously you can substitute epsilon equal to 0, then there is no fun. But the fun is because G is a circuit with epsilon as a constant, so 1 over epsilon is there. And then you cannot just, in that local edge, you cannot just say 1 upon 0. It's infinity. But what may happen is two infinities may cancel, right? There might be 1 over epsilon minus 1 over epsilon. So it's infinity minus infinity and it's 0. So those things are happening now inside. And be as it may, ultimately it gives a polynomial free of epsilon. That's f. Okay, so if you can write your f like that via practical circuit, then we say that f is approximately practical. Yes.
In your circuits that you have divisions?
Yes. So but the division is limited only to epsilon functions. So yeah, so I should say, and I will, I think, say that this is, so your field, if it was F, I mean, or K maybe, this is gone. No, it isn't important actually. No, so whatever was the field, say the field was a big K. So now instead of big K, it is, the epsilon is there. So it is K epsilon. It's the function field, yes.
Do you want to show that example of the example of this computation?
Yeah, I think I will have a picture. Yeah. So it's the function field. You have a base field. In all the previous slides, we had a base field, and on the base field now we have epsilon also. So formally, this is called the function field of epsilon. So there is not only 1 over epsilon, but there may also be 1 over epsilon plus epsilon square. So you compute a polynomial in epsilon and then invert it or take the reciprocal. Okay, so all those things are happening now. And then when you try to take limit, somehow limit is defined. So this is again a very exceptional situation. Limit usually will not be defined because 1 over epsilon will become infinity. But the circuit for G is such that somehow things balance out and the limit is defined. And then it eliminates epsilon and gives you only fx. Okay, so that's the polynomial you wanted. So you say that, well, since because of these exceptional circumstances, my f is actually approximatively computable by an algebraic circuit. So yeah, so this bold red part is the border. So what we have defined is the inside part. Till now, VP, VNP, VBP, etc. are polynomials in the inside. That's the domain D that we have defined of computation. And now actually we are introducing epsilon so that we are actually introducing these paths. We can take a path. So epsilon takes some value here, let's say a real value, and then it gets smaller and smaller and smaller. And when it reaches 0, it probably gives you something new outside the domain. So that's the border. Okay. So epsilon is the way to actually traverse this path, go to epsilon equal to 0, and then get something new. New you will get only when you are dividing by epsilon. Yes. Oh, G is just a VP circuit over the function field in epsilon. Base field has changed. Everything else as in the previous slides. But just whatever, so if you are working over, let's say the finite field F5, finite field with 5 elements, F5, so in F5 you introduce epsilon, look at the function field, and then look at VP over that. Yeah, so that's the idea and the definition in the same place. Yeah, so algebraically, well, okay, so the idea is not complete because I am showing you this path in a picture. So it seems that epsilon has to be real because otherwise, how will you define this limit business, right? So this picture is inherently a real picture. And in computer science, we don't like real fields. We work with unreal fields like these finite fields and other more complicated things. So our definition has to be field oblivious. In particular, it should work for F5. finite field with 5 elements. So in that case, this picture is wrong. But as you know, algebraic geometry is the way to prove theorems using wrong pictures, right? So the wrong picture is this. The correct formula is, yeah, so this is an example that Raphael wanted. I don't know whether it helps Raphael because these things are here actually undefined. But yeah, so you need more constants. So you have already this -2 by epsilon, which is actually undefined under the limit epsilon equal to 0. Then you have 1 over 1 plus epsilon, which is actually defined under limit. And you do all these things, and then ultimately hopefully you get a polynomial that is only dependent on x1 and x2 and free of epsilon and free of infinities also. Right? So when that happens, then we can say that this approximatively computes your bivariate polynomial in x1, x2. So that's how it will look. Same thing as before, except that constants are richer. Right? So constants are now could be extremely complicated in epsilon. We are silent on what these constants are. It could have been epsilon to the 2 raised to 2 raised to 1000, right? Very, very big degrees and very, very big space may be needed to actually put these functions. But again, we always ignore the constants in algebraic computation. Yes.
Example, that's sort of something interesting.
That example, no, it's not interesting. Oh,
And that it showed that x squared y.
okay.
That one is the easiest example.
Yes. So I have to listen to Raphael because I don't remember that example. So what is that? X square y. And then you have 2 cubes. So which is what? X plus x cubed.
Minus, sorry.
X plus epsilon y.
Yeah, exactly. Cubed.
Okay.
And then you divide by epsilon.
And maybe 3 also.
Yeah. And then there's a minus on the other side.
And then you can take epsilon tending to 0. So x cube, yeah. So basically minus x cube, and that is plus, I think. Yeah, so you have this interesting example. Okay, so why did we look at x square y? The reason is that, and let us say this is happening over F5. Okay, the field is F5. So there is no problem in dividing by 3. 3 has an inverse, or it can maybe happening over complex. Sorry?
No, that's good.
Yeah. Yeah, so this is the expression we are taking limit on. Point of this example is the following. If you remember your high school algebra, x square y cannot be written as a combination of 2 cubes. Okay, because it has this weird, it's a weird mixed monomial. So you can write things like x plus y cube is obviously a cube, and then x plus y cube minus x minus y cube is some polynomial, but it's not a monomial. So these mixed monomials you cannot really write as sum of 2 cubes or linear combination of 2 cubes. So to resolve that problem, we take border. So what we do is that we introduce again that blue path. To create that path and reach somewhere outside the domain, we look at x plus epsilon y, take that cube, subtract x cube. So what you get is 3x square epsilon y. And you will get 3x epsilon y square, and you will get epsilon y cube. So the difference is these 3 terms, which doesn't look very good because it seems that yet x square y is corrupted by those terms. But then you observe that if you divide by epsilon, epsilon remains in these 2 places, and then you can kill epsilon. So you will isolate this monomial that you wanted. Okay. So where your high school algebra says impossible, now things are possible. Okay. So with epsilon, new things start happening. I did not want to give this example because this talk should be more complicated than this. Yeah, because this talk is actually about something much more complicated that happens, which is in computation, the epsilon division that is happening, that can be of an extremely large degree. So that is not visible in this high school example. Because here the degree of epsilon is just equal to what degree of x squared y is. That is 3, and this is also 3. These things somehow are not interesting for the talk. So the place where I live is actually much, much more complicated than these examples. But anyways, thanks, Rafael.
Your high school is much more advanced than ours.
No. My high school was pretty bad.
They were practically in undergrad, so we had high standard of the high school, but
Sure.
yeah.
Should not say much. Okay. So should I remove this, or do you want to ask questions? Okay. Yeah, so when you take these paths, these blue paths, then you necessarily get, well, not necessarily, but you expect to get to new places, but those places are not very far from the original domain. So we call it border. Yeah, so let's look at the algebraic way. So algebraic way for computing, well, let me write the whole thing. So algebraic way to compute this desired polynomial f, which is n variate in x1 to xn, is the following. I've already given you the rough idea, I mean the kind of real analytic idea, that you want to write f as limit of a VP circuit over a function field in epsilon. Algebraically, I will remove this real analytic idea by saying the following. I'll say that G should be, I mean, it has a circuit representation which is small, which is doing divisions possibly by epsilon. But ultimately, it should compute a polynomial in epsilon. Okay, so ultimately, it should give me a polynomial in epsilon free of any division. So this might be confusing, very confusing for beginners, because what I'm saying is on the left-hand side, the circuit that you have is doing division, but on the right-hand side, it is free of division. Okay, this can happen. It looks like contradiction, but it can happen because the circuit ultimately computes with these complicated constants. Things cancel out, then things also divide, and then ultimately the denominator is 1. Right? So denominator is epsilon free. That can happen. So that's the exceptional circumstance we are trying to capture in the definition. So left-hand side, the circuit is doing division by epsilon, but the final result at the root, which is here, should be only a polynomial in everything. So x1 to xn and epsilon, it should be a polynomial, no divisions. And then limit is nothing but setting epsilon to 0. Right? So when you are computing this by a small circuit, then you should just set epsilon to 0. There is no problem. You don't need real analytic ideas for that. So limit in this talk will just be a suggestive expression to say that epsilon is equal to 0. Just make that substitution, okay, with this assumption. So it's basically giving you the G sub 0 part of your circuit. There is a small circuit over the function field, and then the G sub 0 part of that is my polynomial. I say that that is being approximately computed. Approximation is a perfect word for it, because if you, again, real analytically, if you think of epsilon as a very, very small real number close to 0, then G0 is kind of the dominating value, and all other values are extremely small, because epsilon, epsilon square, epsilon cube are of lower order. So that's the error term, right? So main term is G0, and the error term is G1, epsilon times something. So epsilon times something is the error term. So do you agree that this is now approximative or approximate algebra computation works over any field, right? This is not, doesn't require real or complex analysis. Okay, so that's the the fourth model of computation. And yeah. So just a warning that this thing doesn't mean that in the circuit you could have just substituted epsilon equal to 0. Because if you did that, then the circuit is actually not just a polynomial. It's by circuit, I mean, we mean this representation. So in this, the edges may be undefined. So you can't just put epsilon equal to 0. That's the problem. You have to basically, so there is a notion of time here. You have to wait till everything is computed at the root. If you are impatient and you in the middle go and substitute epsilon equal to 0, then impatience may lead to failure. Okay, so you have to wait all the way to the end, and then epsilon is cleared, and then you can substitute epsilon equal to 0. Okay, so now such polynomials f are called, they comprise or define the class VP bar. Okay, so that is VP bar. Now, why do we put bar on top of this? How is this a closure? So there are three more interpretations. One of them is that of closure. So in algebraic geometry, there is this notion of Zariski closure. So you can show as an exercise that what we have done here is the same thing as you take VP polynomials think of them as a set of points in the space of polynomials. And those points, you do a Zariski closure on that. So when you do Zariski closure, it's defined over any field. When you do Zariski closure, then you will get VP bar. Okay, so this is the algebraic geometric interpretation. It's not for everybody, but if you like it, you can take it. Okay, I will avoid that interpretation in this talk. And that is why we call it border. Yeah, and then analogously, we can now define size of the polynomial. So the approximative size or approximative complexity of my polynomial f is whatever was needed for G. Okay, so G is a VP circuit. So whatever is the size of G, we say that that is the size bar of f, right? So in particular, so Peter Burgesser was the first one to define approximation this way and show all these 3-4 interpretations that they are equivalent. And also show these connections. So so that's the part I was referring to before, which is very different from that simple example you saw. So G here is has this unknown parameter, which is epsilon to the m. Epsilon goes up to m. Now in the definition is silent about what m will be, right? Because the constants here they are by definition, they are arbitrary. So they could have, for size s, this could be epsilon to the 2 to the s, epsilon to the 2 to the s, 2 to the 2 to the s. Right? It could be very complicated, doubly exponential function. So that could be what this m is. It could be 2 raised to 2 raised to s. But Burgesser using some algebraic geometry results, which actually come from Bezout degree bound in abstract algebraic geometry, using that he could show that the m cannot be bigger than this. Okay, so m is not, you don't need to take m any bigger than 2 raised to, it's here actually, 2 raised to s square. You don't need to take m any bigger than 2 raised to s square. So whatever you can do with larger m, you can also do with m 2 raised to s square. So in other words, m is only exponential. It cannot be super exponential. So that's a major theorem. You cannot see it immediately here. Why should it even be conjectured? It's not clear. Because the definition here was completely arbitrary on epsilon. So why should you get a bound like this? Yes, I will not go any further in this, just the statement I'll read. So the approximative size or complexity is smaller than the exact size. obviously. And the harder part is that the exact size is smaller than an exponential in the approximative size. Because once you know that epsilon to the m is at most 2 to the s square, you can do interpolation. So when you know how big your polynomial is, you can interpolate and extract G0, right? Because ultimately you only wanted G0, not everything. So you can just extract out by paying the cost of m. And m is 2 raised to s square. So s is, in our case, this. That's s. So in 2 raised to s square, you will anyways get an exact circuit, right? So you have upper and lower bounds, but there is the exponential gap. And that is the best we know. So the open question is whether you can do better, whether VP is equal to VP bar. Anything that can be approximated can also be computed exactly. That's the conjecture. So is approximation practical? That's the open question here. I think here the consensus is missing. Probably half of the people think that it's false. Approximation should give you more. But I'm on the other half. So I believe that these two things should be equal. And I'll give you some toy instances where we have shown this to be true. Yes.
So just if I understand the conjecture is that it's that you don't really get any computational efficiency improvement by these.
Correct. Yes, yes. So actually the conjecture is not really saying that m is small. It's silent on m. So m can still be very large. But once such an expression exists, then a small circuit should also exist. That's what it is saying. Oh, I mean, it can also be false. So this is, I am just putting my bias there. But this may be completely false. Either way, it's not known. Okay. Yes.
Is that along with the Turing machine going of a statement like this?
I think there are many analogs, right? There is this whole area of approximation algorithms.
Approximation algorithms to try and approximate NP problems to try and get.
No, but in SDP, so when you are working with rational or real numbers on which have to be actually rational, then they truncate it. You have a floating point representation, you truncate. You say that instead of 100 digits, I'll only look at 10 digits. Yeah. So here also a similar thing. The epsilon is kind of the epsilon requires exponential precision because, I mean, to begin with, epsilon required unlimited precision because there was no bound on m. With this theorem, epsilon requires merely exponential precision. And exact will require poly precision, polynomial in S precision.
And I guess another analog, but not really to say is BPP versus P, right? Because here he's saying it does approximation value anything. And the BPP versus P question is like this randomness value computation, right? That's kind of a similar flavor,
Sure.
but very different.
Yeah, so there actually the answer it is exact computation, but the answer is wrong. So in the probability case, it's, the error is happening actually not on the exactness, but in the final answer. Here, every step of the computation is wrong, but somehow the answer is somehow close to the correct answer. Yeah. So this is actually more wild. The P equal to BPP, people believe more, much more. This is a wilder thing because here, almost every step here is actually wrong. So why should that be corrected to an exact computation? Okay, so yeah, so those are that's the, it's an overview to all these, there's a spectrum of polynomials, right? So we have this practical or linear algebraic or explicit polynomials, and then we have polynomials which can be approximated, and then we have polynomials which can count. That's the exponential sum. And then there are polynomials which are none of these, so they are much, much harder. And most of the polynomials are of that type. They are very hard. They don't fall in any of these categories. So I could discuss some results after this. The time is actually already up. You can ask questions, and then I can give some results, just theorem statements and ideas. Yeah.
There are, I think, problems that are known to be
Yes.
Are there functions that are?
Yeah, good question. Yeah, so next slide, I'll show that. And then what results we have. Yes, so that's a very good question. I motivated all the classes with good examples, but it's not clear right now what is an example for VP bar that is motivating, because the one I was forced to show on this board is kind of useless, right? Because who wants to compute x square y? Nobody. So nobody. So that is not an example for VP bar which is convincing enough. So I'll give you a tough example, which is still widely open, and actually it's a very practical question. So what is a motivating problem in VP bar? So that is the question of factoring circuits. So once you are clear about what class you want to study in your lifetime, you can now ask questions on that class. So let's say you like VP. So now you have given a VP circuit. Can you factorize it? It's a polynomial, right? So polynomials can be factored uniquely. So can you find a unique factorization? That's the circuit factorization problem. And by finding, I mean either practically you factor on a computer, or show that small factors exist, right? So either constructively you do it, or you do it existentially. Maybe it's very hard to find it, but at least they exist. All factors are small. So that is the question of whether the VP class is closed under factors, right? That's an existential property, but yet you want that in many of the applications actually. Because if they don't even exist, then obviously you will never find them, right? So that's at least a first step. This question, what I have written here, is a bit more complicated, because here I am only saying that fx of size s. Okay, so the degree of f can be exponential. Because if you just say size, you start with a variable x, then you square it, and then you repeatedly square it s times. So you will get to x to the 2 to the s, right? So just with this assumption, the degree of f can be 2 raised to s or more. And those polynomials then could have exponentially many factors. So you cannot list all of them. That is one problem. Other problem is more fundamental, which is it might be impossible for all the factors to be easy, right? Most of the factors may be impractical. So let's see an example. So look at this famous example, which I just said, repeated squaring s times. So x to the 2 to the s minus 1. Let's say this is over complex. So you have 2 raised to s. It has 2 raised to s complex roots. Although they have this cyclotomic nature, but if you pick a random subset of them, it is pretty wild, right? So if you take, let's say, 2 raised to s minus 1 of them, or even 2 raised to s minus 1, 2 raised to 2 exponentiated s minus 1, that many of them, half of them if you take in a random way, and then take their product, it will be pretty wild. There is no reason why it should have small circuits, right? So because you have a set of size m, and you are picking a random subset of size m by 2, even if the set m was very structured, m by 2 random subset will be totally arbitrary. So when you look at the polynomial with those roots, it will be exponentially hard, and you can even prove it. I forgot, I should have mentioned the reference. So there is a result that most of the high degree factors of this are actually complicated. They have high circuit complexity. So to make question more amenable to attacks, we have to limit the degree of the factor. So we'll only look at factors of degree polynomial in S, or say S. So this size S circuit is there. Degree may be exponential, but we only want factors H whose degree is S. Okay, so this is small degree. So which in this case is trivial, because if you are taking factors of degree only S, then you are just picking S roots. Even if they are generic, the size of the circuit is only S, order S, right? Because you are just, that circuit obviously exists. It's a univariate factor. So that obstruction goes away. And now you have two parameters, so size of the input circuit and degree of the output factor. And then you can ask, wait, that's going in a different direction. So yeah, so now I can ask whether the factor, any factor of this type, degree D, is the size of H S times D, poly in S times D. Okay, in these two parameters, is it poly? That's what we'll now ask. That's the open question. Okay, so yeah, so actually, okay, I wanted to motivate in another way circuit factoring problem. So this is basically the Newton iteration picture. Factors are important because you can think of instead of factors, you can think of roots. Okay, and for roots, there is this major formula which Newton invented or co-invented, which basically starts at some random point on the x-axis, x0, draws a tangent, then looks at the tangent intersection with the x-axis, again at the appropriate point, again draws a tangent, and so on. So this tangent drawing ultimately converges to the root, which in this case is C, right, where the curve or the function intersects the x-axis. So there is a nice formula which basically uses the first order derivative of your function at the previous approximation to give the next approximation, right? So that formula is key actually in this business. We use that formula also to compute factors. Okay, this is how circuit factoring is done. So that is the algebraic way to compute. Basically, this was given for real roots by Newton, but then it can be made algebraic, and then it can be applied to algebraic computation. Okay, so algebraic circuits can also be factored using the same formula. There are a lot of details here, so I will not even attempt to go into those details. I just want one detail, one point, which is Newton gave this algorithm assuming that the root is simple, multiplicity 1. Okay, and then there are other variants when the root is not simple, that is multiplicity 2, 3 or more. So point being that for higher multiplicity roots, the thing becomes more complicated, even in real analysis. Okay, Newton iteration itself starts failing badly. So that is the problem we face in circuit factoring also, that if the factor H is simple, then things will be simple. But if it is not simple, and especially it has very high multiplicity, which can be as big as 2 raised to S, by the way, in that case, Newton iteration is the only method, but then it badly fails. So this question is open. Okay, the circuit factoring question is open currently. So open question is size of this factor poly SD? That is Bjorgisser's factor conjecture. So this problem has an approximate solution. Okay, so after this long prelude, I can now answer the question I was asked, that this is the problem which is in VP bar. H will be VP bar. And we want to show that H is in VP. That's an open question. So this is a beautiful and probably the only known example where VP bar and VP look separated. Is this clear? Any questions? Yes.
So morally speaking, this is something that we know, like an efficient scheme, which is Newton's approximate root, but then it's the same that we can actually find it exactly in the algebraic case, also efficiently.
Yes, so I'll sketch Bjorgisser's proof. So Bjorgisser's algorithm adapts Newton iteration to give a approximative, I mean, write the factor H as an approximative circuit, but we don't know how to make it exact without a blow up of exponential size. Yeah, I'll sketch the idea. It's not very difficult. I'll remove all the technicalities and just the main thing. But yeah, any other general questions before I go into that proof? That proof is actually important for the results I wanted to present. And anyways, I think it seems that it's also independently interesting for you. So Bürger's theorem is that this factor H or any factor H of a circuit can be written approximatively in just poly size. Poly in both the parameters, remember, S and D. So how does that work? So the trick is, Bürger's trick is to use a perturbed version of Newton iteration. So the perturbation will happen by epsilon. Okay, so epsilon, remember, in our talk is never a real number. It's always a formal variable, right? So introduce a formal variable epsilon. And the setting is that you are given F as a circuit, size S, degree, let us say 2 raised to S. And you are interested in a factor H, which has a multiplicity E. Remember, this is the only case when Newton iteration fails, right? That E is large. So in our case, E is very large. It can be 2 raised to S itself, super poly in S at least. And then there is a cofactor Q, which is co-prime to H. Okay. In fact, we'll simplify this even further for the sake of presentation. Let us take H to be just x1 minus alpha. Okay, it is just when you kill the variables x2 to xn, you are left with just x1 minus some constant, field constant. So let's take that simple case. So H is just a linear factor, but an extremely high multiplicity. So in this case, there is no way you can make Newton iteration useful to give any useful result. So instead of looking at this F, Bürger's proof perturbs it by a formal epsilon. So the perturbation is of this type. It's sort of a derivative of F. Okay, so what it does is it perturbs F by epsilon in x1, and it subtracts the same expression with x1 fixed to alpha. Okay, that is basically mod H. Mod H, this is x1 is alpha, so you look at alpha plus epsilon. And then you can see, I mean, forget about x2 to xn variables for now. So what is happening is that you are just taking the difference once you have x1, other time you have alpha. So you can see that x1 minus alpha is a factor of this, right? So this is kind of derivative, formal derivative with epsilon being formal, and H is a factor of this. This you can see directly from the expression. But H is simple factor. Okay, that is the beauty. So you have a polynomial whose factor is H, but H is simple. So then you can kickstart Newton iteration. And when you kickstart Newton iteration, you will get H. Yeah, so H is a simple factor of F prime. And then you use Kaltofen's factorization algorithm. So Kaltofen has a factorization algorithm which is inspired by Newton, making it algebraic. And
Single factor Hensel lifting.
Yeah, Hensel lifting is also inside. Actually, Hensel lifting, Newton iteration, and implicit function theorem, they are somehow all equivalent. So there are multiple interpretations and hundreds of papers on this. So you use one of them, and the point is that in general, H could have been complicated. I mean, here I'm just saying X linear, but in general, it's a complicated factor. So for that, you have to really use Kaltofen's full scale machinery. So that machinery will give you the simple factor H as a circuit. Okay, so do that. But what have you achieved? So you have actually achieved H with epsilon being present. And if you think of this thing as derivative, so this is like, so x1 to the e, right? So x1 to the e, when you will take derivative, you will get x1 to the e minus 1. So and then you have epsilon present. So epsilon actually appears with degree 2 to the s. And Newton iteration has a formula where derivative divides. So epsilon to the 2 raised to s divides. Okay, so inside all this, which is around 10-20 pages of calculation, ultimately you have an expression where there is a small circuit for h, and epsilon to the 2 to the s is dividing in the edges as constants. Okay, so that is what you have got. So you have actually got h approximatively, and as epsilon tends to 0. Yeah, so that means that you have shown size bar h poly-ST. Okay, are you convinced? Well, I am not convinced, but now you can go back home, and after several days you can see the long proof. So this thing is standard since Purgis's time, and then we don't know what to do without epsilon, how to eliminate epsilon from this. So the reason why I gave this sketch is there would have been no problem if multiplicity was small. So if multiplicity is poly, then this whole business you can actually eliminate epsilon. But if the multiplicity is super poly, then you don't get anything except approximatively, right? So this I feel is the most important problem also practically, and we can only approximate it. We don't know how to do this exactly because it has roots in Newton iteration, and there is no good fix for this known, especially in exponential super poly degree cases. Yes, so it gives the factor in VP bar but unknown in VP. So the question is whether circuits are truly closed under factoring. Any questions? Okay, so should I conclude or should I go on and bore you with more details? What do you think? What does Rafael think? Because I have to listen to him. Okay, so I'll just give, because this I think can be understood generally without going into the details. So the question is, where does VP bar live? The problem is that in the definition, this epsilon appears with exponential degree, as we have seen in the motivating example also, that epsilon truly appears with exponential degree and you cannot eliminate it. So, I mean, at least you don't know how to eliminate it. So then, is it possible that VP bar is computing polynomials which are not even explicit? Right? Is it outside VNP? So because VP bar and VNP comparison we have not done. I mean, they seem to be incomparable. Both of them contain VP, but we don't know whether it's like saying whether SAT can be approximated. Right? So satisfiability, we don't have approximation algorithms because it so happens that the approximation algorithms for SAT are themselves SAT hard. Right? So there that loop kind of is vicious. So here is it even worse. Here is VP bar computing not only SAT but something even harder, or is it just computing something harder but it cannot compute SAT? Right. So all these comparisons are there, which we have no idea of. So where does VP bar live? It is open whether VP bar is in VNP, and these kind of questions I'll call debordering. That's the term we have invented in our papers. So debordering is essentially making approximative things exact by hook or by crook. Okay, so you may have made it exact efficiently, or you have made it exact in some bigger class like VNP. So the whole spectrum of VP to VNP. In fact, it can also be the sub-exponential part like Vn sub-exp. It can even be that. Because we don't know anything other than V-nexp. I mean, because epsilon has degree exponential, so we only know exponential debordering. We don't know anything sub-exponential. So all those questions I'll call debordering questions. So we recently gave a special case of VP bar, where these constants, we said that, well, there is no point looking at allowing these constants to be arbitrary functions in epsilon. Let us say that these functions are also circuits. Okay, so there is a circuit of size S on which the edges have constants, but let's not allow the constants to be arbitrary. Let's say that they are also given by circuits of size S. Okay, which is a reasonable demand, because if you actually wanted to fabricate this in practice, nobody can fabricate an arbitrary constant, right? The only way to compute this arbitrary constant on the edges is again via a circuit, right? So you should think of the constants also as circuits. In other words, the overall thing is a circuit of size S with x1 to xn variables and epsilon. So take all the variables, including epsilon, have a big circuit of size S, and then whatever it gives is your G, right? So that we call presentable border. So presentable border is basically constants are made presentable. They are circuits in epsilon. And then overall you have a size S circuit with epsilon and x's as before being the input variables. And we give it a fancy name. So this is VP bar sub epsilon, which means these are actually border circuits where epsilon circuit is also in epsilon. Okay, so circuit is not only in x1 to xn, but it also includes epsilon. It has n+1 variables. So that doesn't preclude the degree of epsilon being exponential, right? So the circuit is basically biased. It keeps the degree of x1 to xn polynomial in n, but for epsilon, it is allowed to do repeated squaring. So it can go to 2 raised to n, right? So it is biased towards epsilon, but still, overall, it's a circuit of size S, which itself is poly n. Yeah, so that's the understanding. And what we showed is that this VP bar epsilon is actually in VNP. Okay, so if you make the border presentable, then it becomes explicit. So that is not the proof. Yeah, so read this as presentable is explicit. So when you have a presentable border polynomial, then it's actually an explicit polynomial, which practically solves the problem, because in practice, the border polynomials that you will see will be presentable ones only, because non-presentable by definition are non-presentable. Like you will never see them in practice.
The ones in factorization, for instance.
Yeah, exactly. So our motivating problem gets explicit, because Newton iteration is something very, very presentable. You have explicit formula, Newton's formula, where you are dividing by derivative. Derivative itself has a circuit, which is a circuit in epsilon. So overall, when you unpack this, you have a factor, the factor h in the previous slide is actually in VP bar epsilon. It's a presentable border polynomial h. So those factors are actually in BNP. Okay, so any circuit, exponential degree, small size, when you look at low degree factors, they are presentable border and hence they are explicit. They are in BNP. So we partially solve Bjorgeser's factor conjecture. There are many footnotes or fine print, which I'm skipping, but I guess you get the general idea. So presentable is explicit is one result. Then sizes circuits have degree S factors, all of them in VNP. That's a result which is a corollary, as we just discussed. And the reason is that Bjorgeser's perturb Newton iteration, it gives actually a presentable factor circuit. And yeah, and then see the techniques which we used, they also show that VNP is closed under factoring over finite fields. This was an open question for finite fields, that if you take a exponential sum circuit, what can you say about the factors? And over finite field, especially. That was an open question. So the factors are again exponential sum circuit. Okay, and the case here, which for the reason why it was open, the reason why VP is still open. So VP, we don't know whether the factors of VP Whether practical circuits over finite fields have practical factors, that is still open. But the previous result tells you that the practical circuits over finite fields have only explicit factors. Okay, so they can't be non-explicit. The case where why all these things were open and VP is still open is because we don't know how to take square roots of a square mod 2. Okay, we can't do inverse Frobenius. So when characteristic is P, we don't know how to do F to the 1 over P, given that F is actually a pth power. And in this case, given that F is a square, we don't know how to take square roots. The problem is, again, it is as old as Newton because although Newton iteration is for real, which is characteristic 0, if you run the same thing in characteristic P, the place where it fails is when the multiplicity is a multiple of P. Then it completely fails. Nothing can be done because the whole business actually is by dividing the derivative. So if you divide by P, you are dividing by 0. So then actually there is no idea whatsoever what to do in that case. So this is the example you should remember. So we have shown that our result is that square roots mod 2 can be computed explicitly, but are they practical? That we don't know. And yes, so these are the questions now. All these classes come together. So what we conjecture is VP is equal to presentable border is equal to border, not equal to exponential sum. Right? So we conjecture that, or we ask that is approximation practical, and is it presentable, and is exponential sum impractical, and also non-approximable, can't be approximated. Yeah, I think we should just. So the toy examples for lower depths, I think that was all extra. Let me just put that online. Let me skip it for the talk. So in conclusion, so what is the limit point of this study, right? What is the border of our border in this talk? So let us just finish that part. So the things that I have skipped, they are results actually about debordering, about proving lower bounds, and proving whether a circuit is 0. That is called identity testing. And we can ask similar questions for other toy cases also. Let me skip this part for now. One thing that is open, it emerges from the toy case that I have skipped, is that if you look at depth 3 circuits, so remember depth was an important parameter. So you have basically addition of multiplication of addition gates. So that's a very small model that you can study. What is the border of that? Right, that we don't know. So we don't know as in we don't have any idea whether it is in VNP. And surely we don't have any idea whether it is in VP. Okay, so it may be, so first you show that it's in VNP. And then you try to show that it's in VP or even easier. So those are the open questions. So there are many, many toy examples where you can try this debordering trick. In general, is border presentable? That's a question I already asked. And if it is presentable, then it will become explicit. Both these questions are open. Circuit factoring is open. We have shown that Burgessler conjecture with VNP, but is it actually VP? Right? Not just explicit, but even practical. Is there a way to adapt Newton iteration for exponential degree circuits? That we don't know. Yeah, and you can see the details. Thank you.